So in the previous topology video, we defined a topological space. So the next natural thing to do is to consider some examples. So this is the first one, example 1. And the set we have here is the set X consisting of the 3 objects A, B and C. And in fact, on this single set, we are going to consider 9 topologies and 2 collections, 2 additional collections, which you will see are not topologies. So we are going to see some examples as well as 2 non-examples. The first topology is this one, T1, consisting of the set X and the empty set and nothing else. Now, to understand this, a schematic diagram is also available here. It is given in the text. Understand this means to understand the collection. This may at first sight seem like just the Venn diagram of X, because you see the set X and you see the elements in X drawn like this, but actually this is supposed to show the collection like this. In what sense? That you should be able to see what the sets in this collection are here. One of them X you obviously see, and what about the empty set? We do not draw anything special to indicate that the empty set is in the collection. So we are adopting the convention that whatever collections we are going to consider, this one and the other subsequent ones, the empty set will actually always be there. So we are not doing anything special to indicate that fact here in this diagram and the other ones which will come with the other collections. Okay, now I said that this is a topology. How? Let us bring back the axioms from the definition and see one by one the requirements. What was the first one? The first one requires that the collection have the empty set as well as the entire set. That obviously is true here for this one. Okay, so that one is okay. What was the second one? The second one asks us that the collection should be like this, that if you take any number of sets, any sets from the collection, you take their union, the union should again be an element in the collection. Now, in the unions that you can form, actually there will be many possible unions that you can form where the sets involved are X and or the empty set. Do not forget that you can take copies of the same set when you are considering a union. Say you take 5 or 6 copies of X and say 3 copies of the empty set, and you take their union. Or you can actually take just the empty set itself and you take the union. It sounds a little silly, but you can consider the union of just one set. Okay. Or you get my point. There will be many unions, but because the distinct sets involved in all those unions are these two, so the union will either be equal to X or equal to the empty set. And in fact, we can see in what situations we are going to have X and when we will have empty set. When you just have the empty set or copies of the empty set as the sets in your union, then the union will be the empty set. But if at least one of the sets in your union is X, then the union will be equal to X. And in both the cases, the union obviously is again here. So the second requirement is also true. Next comes the condition that all finite intersections of elements of T1 are again elements in T1. Is that true? Again here we can have copies of these sets when you are considering finite intersections. But this time you will consider only finitely many sets at a time. So in all these possible intersections also, we will have either this or this. How? If at least one of the sets in your intersection is the empty set, then the intersection is equal to the empty set. You already know why from set theory. But if all the sets involved in the intersection are equal to x, then the intersection is x. And do not forget that now we are considering finitely many sets when we are talking about intersection. But anyway, so the third requirement is also true. So yes, this is a legitimate topology on x, and x with respect to this topology is a topological space. Let us see the next collection. The next one is this T2. Here also we have x as well as the empty set, but besides them we also have the singleton set consisting of A and this pair set consisting of the objects A and B. And now you can see that the diagram has also changed. So besides having x and empty set, you also have the set, this pair set consisting of A and B and the singleton set. Okay, so to indicate those sets here diagrammatically, we have used these elliptical these regions. So this is another topology on that same set x. So the first axiom of course is true because x and the empty set are both there. What about the second axiom? The second axiom isn't really as easy to verify now as that other collection T1. But anyway, so if you consider a union, an arbitrary union of elements of T2, what will possibly happen? If any one set in your union is x, then of course the union is equal to x because everything is a subset of x. Alright, there is one more observation. There is actually no point considering the empty set as a set in the union because it's not going to affect anything. Unless of course you are only considering empty sets as the sets in your union. Then the union will be the empty set. Alright. What will happen if, say, x is not there? Because if at least one x is there, then the union is x regardless of what the other sets are. So it does not really matter. So now say you do not consider x as a set in your union. Also we have seen that there is no point considering the empty set unless all the sets are the empty sets. So these two cases have already been settled. That means we can now consider that our sets do not have x, and also all the sets are not the empty set, and even if there is an empty set, you can just forget about it. That means essentially you are just considering these two sets and their copies in your union. So what will happen? If all the sets are equal to this singleton set, then this itself will be the union. But if there is at least one set which is equal to this, then this will be the union. And in all these possible cases, the union always, every time, is inside T2 as an element. So the second condition is also true. How do you verify the third condition? This time you have to consider finitely many sets and you are going to intersect them. If at least one of the sets in your intersection is equal to the empty set, then the intersection is the empty set, which of course is here. That means now we can consider that none of your sets in the intersection is equal to the empty set. All of them are non-empty. Okay. This time, however, if all the sets in your intersection are equal to x, then the intersection is x. Otherwise, you can ignore x. So the roles of x and the empty set, they have got reversed. When you consider union, it's just the opposite. You get my point. Okay, you can already see that. So now what are we left with? We are now left with those cases where we consider finitely many sets, none of them is equal to the empty set, and even if one or more of the sets are equal to x, we can just ignore that. All of them are not x. So that means at least one set is this one or this one. Now if all the sets are equal to this, then this itself is the intersection. But if at least one set is this, then this will be the intersection. So here also you see that all the axioms are true. So this is another topology which is bigger than the previous one, in the sense that now you have got these two new open sets, this one and this one, besides x and the empty set. But because it's a different one, so this topology will give you another topological space. X is same, but T1 and T2 are different. So just like when you change the metric on a set from one metric to another metric and you get different metric spaces, so here also you are getting different topological spaces. X comma T1, one of them, and the other one is x comma T2. Next collection T3. This time it's a little bit different. You can see that we no longer have that singleton set consisting of A. Instead, we have the singleton set consisting of B. But the pair set consisting of A and B is still here, just like T2. But there is one more pair set, B comma C. And X and empty set are there. For this one, I won't go through all the axiom verifications. You can see it for yourself. We can, however, still see one or two things that are true here. This collection, for it to be a topology, obviously all the axioms should be true. In particular, the intersection of these two sets has to again be an element in T3, and that intersection is this set which is there. Okay. And what else do you see? If you take the intersection of this and this, the intersection will be this, because this is the subset of this. Same is the case if you take the intersection of this and this. What will happen with the union? If you take the union of this and this, that union will be equal to this, because this is the superset. Same will be the case if you take the union of this and this. This will be the union. If you take the union of this and this, you get x, which is there. So like that, you should convince yourself that this is also another topology. We cannot say that this topology T3 is bigger than T2 in the first sense, in which T2 is bigger than T1, because T2 had the singleton set consisting of A, which however is not present here. Here instead a new element has come. Okay, so these two topologies, T2 and T3, in that sense are not comparable, just like T1 and T2 are comparable, that one is sitting inside the other. But it happens. Okay. So this is another example of topology on X. So you get another topological space X comma T3. Next one is T4. Suddenly the size has got reduced. Now besides the empty set and the entire set X, we only have the singleton set consisting of B, and this is also a topology on X. This one, however, is sitting inside that T3. You see, this B was present there also, but there you had A comma B and B comma C as well, which are not present here now. So here also you verify that this is a topology. See, verifying that a collection is a topology may seem like a daunting task at first. But as you really start to think about it, you will see that you can create some shortcuts. Although, what is the daunting task? The daunting task is to figure out how many possible unions and intersections you can form, and you have to check. But as you start thinking about it, you will see that it's really not that big of a task also. So I want to leave that part to you. Okay. So we just accept for now that this is also a topology on X. So you get another topological space X comma T4. Next collection is T5. Here besides X and the empty set, we have the singleton set. So that set again came back, consisting of A and the pair set B comma C. So this is another topology on X, and you get another topological space. This one also you verify. Next, T6. In T6, besides these two sets, we have the singleton sets consisting of B and then C, and also the sets AB and BC, AB and BC, and B and C. So this is another topology on X. Next we have T7. In T7, besides these two sets, we only have the pair set A comma B. This is also a topology, another topology on X. And we have two more. So the next one is T8. In this one, we have the pair set A comma B and the singleton sets A and B. This is also another topology on X. And then there is one more. Final one is T9. Actually here we have all the subsets of X. So it is equal to the power set of X, the set of all subsets of X. And the diagram accordingly is very messy to indicate that we are considering all the subsets. First we start with the single elements, and then all the pair sets have been shown like this. And then of course you have the entire set X, and the empty set is sitting in the background. Ironically, in spite of having so much, everything here that you can possibly have in this collection, verifying that this is a topology is almost trivial, simply because everything is in this collection. So you know the fact that obviously these two will be in the collection because this is the power set. Now you also know the fact that if you take any number of subsets of a given set and take their union, that union ultimately is again a subset of X. So that will be present here because all subsets are present. Similarly, any finite intersection of subsets of X is again a subset of X. So this is automatically a topology on X. And now next we are going to see two non-topologies. Next let us consider the collection T10. Besides having the set X and the empty set, we have these two singleton sets. And this T10 is, unlike the previous examples, not a topology on X. Why? One reason is that if you take the union of these two sets, what do you get? You get the pair set A comma B. That is not present here. You can see AB is not there. So the second axiom fails here. So this is not a topology. It's not the case that every possible collection will be a topology on a set. So this is one such non-example. And then there is another one. Next one, T11. Besides these two sets, we have these two pair sets A comma B and B comma C. Now T10 failed to satisfy the second axiom. This one will fail to satisfy the third axiom, because if you take the intersection of these two sets, you get the singleton set B, which is not present here. Okay, so intersecting these two, we get something which is outside T11. So T11 is not a topology on X. let's see what is there next. Example 2. Here we consider X to be any set, not anything specific that consisting of 3 elements or anything. X is just any set, and we are considering the collection of all subsets of X. That means we are considering the power set of X. So it is that T9 from the previous example, and this is a topology on X. Now we know very well why that is the case, simply because you have all the subsets here, and it has a name also. It's called the discrete topology on X, and with this topology X is called a discrete topological space, and the other extreme is this collection, which also we have already seen in example 1 in the form of the collection T1. In this general case also, this is a topology on X, and this one is called the indiscrete topology or trivial topology on X. So these two topologies in a sense are the extremes. This one has as few open sets as you can possibly have, and this one has as many open sets as you can possibly have, and both of them are in a sense not really that interesting. The topologies that we will be interested in will fall in between these two extremes. But anyway, this was example 2. Now let us go to more interesting examples in example 3. Example 3. In this one also X is actually any set, so that generality is there, but the collection is somewhat special. We are denoting it by tau suffix f. F stands for finite, and the elements in tau f are this. Let this be the collection of those subsets U of X such that the complement of U in X, X difference U, is either all of X, or that means it's equal to X, or is a finite set. The original X may not be finite, but this is the condition for a subset of X to be an element of tau f. Then it turns out that this is also a topology on X, and it has a name. It's called the finite complement topology on X because of this condition that the complement has to be finite, and that is why here you see F. F stands for finite. Now let us verify that this really is a topology. Straight away go for the first axiom here. Here we have to prove that the set X as well as the empty set are both in tau f. What is the complement of X in itself? That's the empty set, and the empty set by definition is finite, and that is why by that definition of tau f, the set X, you see, we are not talking about this set, okay? We are talking about this set X difference U, so that U is now X. So because of this, X belongs to tau f. What is the complement of the empty set? That is the entire set X. So in this case, X difference U is all of X. So again, because of that, the empty set also belongs to tau f. So that means axiom 1 is true for this collection. Next we go for axiom 2. For the second axiom, we take any index family U alpha, where alpha varies over the index set I, of elements of that collection tau f, and we want to show that their union is again in tau f. Because we are considering union, there is no point having the empty set in this family, because the empty set anyway will vanish inside the union. So we can assume without loss of generality that each U alpha is non-empty. But these U alphas are coming from where? Tau f. So because each one of them is non-empty, the complements cannot be all of X. For no one of them will it be equal to X. So that means each such complement has to be finite. Alright. Now we take the complement of the union in X by one of the generalized De Morgan's law complement of the union is equal to intersection of the complements. Okay. Now what can we say from this? Note that this intersection is a subset of all these sets. Actually, it's enough to consider one complement from here. This is a subset of X difference U alpha for some particular alpha, which is finite. All of these are finite. So obviously, this being a subset of that finite set will itself be finite. That means this difference is finite. So by the definition of tau f, this will really be in tau f. That's what we wanted to show, right? So we have verified the second axiom also. Let me not again write these things, okay, you already understand. Let us instead next go for the third axiom. For the third axiom, we take finitely many elements of tau f. Here n is a positive integer. Now if some ui from this list of u's is empty, then what happens to the intersection? The intersection will also be empty, which is in tau f. We already verified this fact in when we verified axiom 1. So in that case we are done. So let us assume that no ui is the empty set. Ui is non-empty for all these i's. Then because the ui's are coming from tau f, so all these complements of the ui's in X have to be finite sets. Now we consider the complement of the intersection, because we want to show that the intersection is in tau f. So we consider its complement. Again, by extended De Morgan's law, complement of intersection is equal to union of complements. Now these complements are all finite sets and there are finitely many of them. So if you take their union, you are again going to get a finite set. So the complement of this set is finite. So by the definition of tau f, in this case also this intersection will be an element of tau f. So that is how tau f is a legitimate topology on X. And in this next example there is a similar one, but the condition is slightly different. So let us next see that one. In example 4, we again have any set X, and this time we are considering the collection tau C consisting of those sets U of X, such that again the complement of U this time is either all of X or countable. So the difference is that we have replaced finite by countable. Then tau C, just like tau f, is a topology on X, and it is called the co-countable topology on X. That previous one, finite complement topology, is sometimes also called co-finite topology. Verification of this is similar to the previous one, so I am leaving that to you. Oh, and one more thing, do not forget that in this book, countable means either finite or countably infinite. It has a slightly different meaning in other books. In that, in other books, countable itself means countably infinite. But in this book, that's not the case. Okay, countable is a collective term. It represents the cases either finite or countably infinite. Countably infinite means the set is in a bijection with the set of positive integers. Okay, so you verify this yourself. Now next, let us see one thing that we have already discussed about a little when we were seeing the topologies in the first example. That is where we came across some topologies that can be compared with each other. Some topologies were not comparable, one was inside the other, that type of thing. So we have names, we have some terms for these situations. So that is next. So next we have this definition. In this definition, let's consider two topologies tau and tau prime on a single set X. If tau prime is containing tau as a sub collection, then we say that tau prime is finer than tau, and in this same situation we also say that tau is coarser than tau prime. The reason for these names you will find in the text, where the author has used an analogy between this and stones and pebbles, smashing stones, creating finer pieces. Like first you have a stone, then you smash it into pieces, you have smaller stones, and eventually you get dust. It's given there. In some sense that makes sense. I mean, why these terms were chosen, finer and coarser. But I want you to do that, okay. And there is more in this definition. This is not all. If this containment is not simply a containment, but this strict containment, this stronger containment, that tau prime is a superset of tau, a proper superset of tau, or tau is a proper subset of tau prime, then we say that tau prime is strictly finer than tau, and in this same situation we also say that tau is strictly coarser than tau prime. There are other names which are also there in the literature that mathematicians use. Another set of names is larger and smaller. Very easy to remember, but the author says that it's not as vivid as the names finer and coarser. And you already know what that means. The larger one will be this, and the smaller one will be this. That's it. And there is another pair of names which is very confusing. Stronger and weaker. In this situation, some mathematicians say that this topology is stronger than this topology, and analysts, people who work in analytic areas, like they work in say differential equations or anything analysis related, they are they will do this. They will call the topology having more open sets stronger. Maybe because having more open sets is somehow favorable to what they do. However, confusingly, topologists prefer to call this one stronger and this one weaker. Topologists do not prefer an overabundance of open sets. Maybe that somehow makes the situation less interesting topologically. That is only my guess, okay. So the author says that in this book we are not going to use these terms stronger and weaker. And if you see these terms in some topology text or in some paper, in the beginning itself you have to know what those terms mean. Whether the one having more open sets is stronger or the one having less open sets is stronger, is considered stronger. It's an unfortunate thing with mathematics that this is not the only thing where you have a discrepancy of this type. Many other things in maths are like this. For example, some terms elsewhere, they mean one thing in one place and a slightly different thing in another place. One perfect example is the notion of an integral domain from ring theory. Some people assume that integral domains must have a multiplicative identity. Some do not assume that. And in fact, even if, before going to the notion of integral domains, the notion of zero divisors itself is not consistent. Okay, so unfortunately such things are present in mathematics. It's not like, for example, what you have in biology, in taxonomy, for example, where you have this binomial nomenclature, where there is a rule for naming species, or say in chemistry you have IUPAC nomenclature, where you follow some specific rules, standard rules to name organic compounds, and in fact there are rules for naming inorganic compounds also, IUPAC. That type of thing is not here, unfortunately. But anyway, it is what it is. So after this, in the next section, we are going to see that just like vector spaces have basis, topological spaces also have basis. That using only, instead of entirely giving the topology at once, which is what we have been doing with these examples, you can specify only a small collection of sets, and that collection somehow will generate the topology, just like the basis elements in a vector space generate all the vectors through linear combinations. We will see what these things are. So that will be all for tonight, and tomorrow also, of course, we have our usual upload. So see you tomorrow with something new. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.